The algebraist is a wild creature, finding satisfaction in structure, roaming in free groups and exploring open fields filled with all kinds of mathematical objects. A life of discovery is what drives these beings. Unfortunately, they're remarkably inefficient reproductive organisms, as mates are not often attracted to one's expertise in module theory. However, the algebraist persists and eventually finds another algebraist to settle with for lifelong partnership. Harmony is once again sung by nature, as is clear by the bonding of these two creatures.
What's up, math lads? Welcome to this week's episode of How to Be Smarter Than Your Friends. Today is special because we're moving away from the clusterfuck of jargon that is foundational logic, and we're moving into the algebraist territory. Now, before we dive into the complexities of the topic, we need to get back to basics. Integers are everything in the subject area. Permutation groups, cyclic groups, and finite fields all come after we learn about some properties of integers. So for the most part, we can relax and just talk numbers for once. More specifically, we'll be discussing the division algorithm and prime numbers. The division algorithm may sound like something you learned in 3rd grade, but we're going to dress it up a little bit. It states that if we have two integers, a and b, there must exist two unique integers, q and r, such that a equals bq plus r. Q is what's known as the quotient, while r is the remainder. Also, r lives between 0 and b. Let's take this back to how we might have learned division in school. If we divide 299 by 29, then doing our grade school division will eventually get us to 10 remainder 9. Well, under the context of the theorem, 10 is our q and 9 is our r, so 299 equals 29 times 10 plus 9. Alright, so you already know how to divide, but now you know how to divide. And if the remainder is 0, then we can say that a divides b, or equivalently, a equals bk for some integer k. Nifty. Now, if we're talking about division, we also have to talk divisors. Divisors are any number that divides another number. So 6 divides 12, 4 divides 16, and 2 divides 3,179,362. One particular concern we have is whether or not two numbers share divisors, and moreover, what the largest of those divisors is, otherwise known as the greatest common divisor, or GCD. Let's suppose we have a pair of numbers, and they want to find each other and make sure they're good matches for each other. But they're not sure what they have in common. It's not like numbers have their own dating profiles on OkCupid or something and just list out all their divisors. Let's take 180 and 105. One way we can find out what they have in common is for both of them to spill every vulnerable detail about their divisors. Or even better, we could get Euclid to play matchmaker. First, we divide 185 by 105 using the division algorithm, and then get 185 equals 105 times 1 plus 80. Replace 185 with 105, and replace 105 with 80. Now, 105 equals 80 times 1 plus 25. Replace 105 with 80, and 80 with 25, and we have 80 equals 25 times 3 plus 5. Replace 80 with 25 and 25 with 5, we get 25 equals 5 times 5 plus 0. When the remainder is 0, we stop. So 5 is the greatest common factor. Sounds like they weren't that compatible after all. Back to swiping. So now let's talk about prime numbers. Prime numbers are strictly numbers that have the positive divisors 1 and themselves. So 5 has divisors 1 and 5, 13 has divisors 1 and 13, and 1 is not a prime number. Prime numbers are somewhat important because some of the later theorems we'll talk about rely on the assumptions that the order of a group, ring, or field is prime. Anyways, here's some nice facts about primes that'll probably be useful. If a prime number divides a product of integers, then it must divide at least one of those integers. There's an infinite number of primes, and any number can be written as a unique product of primes. You know, the boring stuff. Anyways, that's the video. I hope you enjoyed. Okay, fine. We'll prove at least one of these. That product of primes thing, by the way, is called the fundamental theorem of arithmetic. So I guess if it has fundamental theorem, then we should probably pay attention to it. So any natural number greater than 1 is prime, or it can be written as a unique product of primes. Suppose there exists a number that isn't prime and isn't a product of primes. We'll call it a and assume that it's the smallest such number. A is composite and can be written as a1 times a2, where a1 and a2 are between 1 and a. Well, a1 and a2 are not products of primes, since if they were, they'd be non-prime factorable numbers less than a, and we said that a had to be the smallest. So a1 and a2 are products of primes. So A has to be a product of primes anyways. Now, as far as the unique part, it's centered around an argument where we let n be two different factorizations, where the primes are in ascending order. We show that one prime, namely p1, of the first factorization must divide some qi from the second factorization. Then we deduce that p1 equals qi, since they're both primes. And likewise, q1 equals pj for some j. Therefore, p1 equals q1, since this inequality sandwich has to be true. If we continue inductively, we'll learn that the factorizations are actually identical, so the factorization of a composite number into a product of primes is in fact unique. You're on your way to becoming the algebraist your parents wanted you to be. Did I say algebraist? I meant doctor. But that's not the only wave of disappointment you'll have to deal with. Just wait until your first exam. Then you have to explain to your professor why you can't be an algebraist either. So, watch more Koshi's Couch, and convince yourself this is a better use of your time than opening Dummit and Foot for the 5th time today with the intention of studying. Anyways, thanks for taking the time to watch this video. If you enjoyed it, please like this video and share it with your friends. Please leave any thoughts you have in the comments down below, and keep learning.